Okay, and we're back. So we did this problem on Friday, right? Okay. During second period, I have 3 other problems done in my notes that I would like to do. Second period chose to do this problem on the video. So I'm going to let you choose. You can either do this, x e to the x, or this, cosine over 2 plus sine x. You got 2 choices. You can either do x e to the x or cosine over 2 plus sine x. Who wants to do x e to the x? Who wants to do the trig? Who doesn't care? There we go. Okay, we'll do x e to the x. It doesn't really matter. I honestly thought the trig one was easier, but
That's why I want you to see all of them.
right.
I'm here to work.
Actually, this one's not even too bad.
If it's easy, then you win.
All right. Your senior quote should be anything less than your best is failure. No lies.
Yeah, never trust a big body smile.
From the song. Ice Ice Baby.
Never trust. No, the Earth's not one.
Yeah.
Never mind. I'll tell you. I'll say it later.
Tell you when you're over. All right.
Well, actually, never trust a big body smile.
So x e to the x. Okay. First thing. What's my domain of this thing? I guess a better question is there any restriction on my domain? It's kind of like a product of 2 different types of functions, right? Okay, just y equals x. Is there any restriction on the domain? Nope. What about e to the x? Is there any restriction on the domain? Domain. You're thinking about the range, right? Right. He said greater than 0. He's thinking about the range. This is just the domain here. So the domain is then going to end up being all real numbers. Because I can plug in anything that I want. The range is going to come into play. All right, let's take a look at part B here. And part B is the intercepts. Right? All right, so for the y-intercept, for my y-intercept, again, that's 0, comma. So when I plug in 0, that's going to be 0 times e to the 0. Right? So y is equal to 0 times 1 or 0 at 0, 0. Let's see if there are any other x-intercepts. Because we see an x-intercept with our y-intercept, but let's see if there's any other x-intercepts. So that's basically like saying x times e to the x equals 0. Set it equal to 0. Well, that's a product. So I can say, well, x equals 0 and e to the x equals 0, which makes sense because that's my x-intercept as my y-intercept, 0, 0. That's where that ties in. But let's see e to the x equals 0. Okay, if it's an exponential, I'll turn it into logarithmic. So log base e, or ln, of 0 is equal to x. So I would go in and say ln of 0. Wah, wah. That doesn't exist. So there are no solutions here. So that means the only x-intercept I have is again at 0, 0. So we know this goes through 0, 0 so far. We know the domain is going to be forever to the left and to the right, but we know it's going to go through 0, 0. Now this is, oh, not yet. Okay, sorry. Part D is where it starts to get a little interesting. Excuse me. Okay, for symmetry, let's plug in, and you know what? I'm going to write the original x e to the x over here. Let's plug in let's plug in negative x. Let's find f of negative x and see what happens. Well, that is negative x times e to the negative x. Okay, so that's like negative x over e to the x. Is there anything I can do to simplify that down? Not really. That's kind of it. Did that turn out to be either negative f of x or f of negative x? No. There's no symmetry here. The left side does not match the right side, and it is not a 180-degree rotation. Okay, this is where it starts to get a little weird. Now, thinking about the two functions that make up our full function, x e to the x. Are there any asymptotes with just that y equals x? No. Are there any asymptotes with e to the x? Think about our parent e to the x. Where is is it a horizontal or vertical asymptote? Which one is it? It's horizontal. So there's no vertical asymptote, which probably means that there are no vertical asymptotes out of this whole thing. And I can confirm that by saying, what's the domain? So there's not going to be any vertical asymptotes. I guess that's a good thing to write down. Okay. Where is the horizontal asymptote for e to the x? At 0, right? At 0. Okay, so my guess is that there's going to be another one at 0. But it's not okay to just guess at it. How do you know for sure where a horizontal asymptote is? Well, you have to take the limit as x goes to infinity of your equation and see what happens. Okay. Well, this is going to be infinity times e to the infinity. Infinity times infinity. So is there a horizontal asymptote on the right side? No, because it's going to keep going up forever. But we also need to check, notice how I said on the right side, negative infinity. Because now when I go to plug this in, this is going to be negative infinity times, what is e to the negative infinity? 0. What do we have here? Oh, whatchamacallit? We gotta go to the hospital, right? No, I'm not joking. I'm not joking about going to the hospital. This is an indeterminate form, right? This is an indeterminate form. So we have to do L'Hopital's rule, where we have to say, okay, let's take the reciprocal of one value. So the best route to take, what did I choose to do? Oh, yeah, because this is going to be, nope, sorry. We started down the path, got to finish it. We got to take the reciprocal of one value to get to the other, right? So I said 1 over. I did that in my notes, so I'll do the same thing. Remember, that's the technique of using the infinity times 0 indeterminate form. Take the reciprocal of one value, divide it by the reciprocal. Okay, so let's reduce that. That's x over e to the negative x. And what we're doing here is we're taking the limit as x goes to negative infinity of x over e to the negative x. Well, in this case, what's wrong? We good? Okay. Yeah. Wait a sec.
Negative infinity, then it's going to equal -1.
No. This should come up to 0. What am I doing wrong?
We have to
X
take,
over e to the negative x.
Wait, Mr. Levin.
we do one more L hospital rule.
What up? So how are you able to just make it x over 1 over?
I just took the reciprocal. I divided by the reciprocal because these are equivalent statements.
Okay.
Okay, in my notes, I made this jump.
Well, you probably do the L hospital rule one more time, but do the derivative because it's infinity over negative infinity. The
Where did
derivative of x is 1. 1 over e to the negative x is 1 over 0. And then it equals 0. That's why I should keep.
Oh, I didn't take the derivative. That's why. I'm so stupid. I didn't do L'Hopital's rule yet. Derp. Gosh. Stupid. Come on, pull it together. Somebody's got cases Mondays.
Bad video to watch.
No, it's just fine. You know, it's good to see the process, right? Because I'm like, how did x go to 1? Duh, you take the derivative. And now when I take the derivative of e to the negative x, chain rule, e to the negative x times -1. Yeah, buddy. Hey, we're not learning. We haven't learned anything new.
So it's negative e to the negative x.
So now I take the limit. Hey, you guys chose this problem. X goes to negative infinity of 1 over negative e to the negative x.
1 over.
And x goes to negative infinity.
It's negative. It's going to be negative. Well,
Now, these two negatives will cancel out when I plug in negative infinity, right? So that's going to be
infinite to the infinite.
1 over infinity, which is 0. All that to say to confirm what we thought. Gross. Sorry.
Why do we have to do that?
Because we only guessed that the fact that it would be like
But you know, sometimes you guess you're right. So like,
Yes, correctly.
okay. All right, let's keep it rolling. So that was part D. Oh my gosh, you scared me.
I'm glad I scared you. Come see me after class.
This is Napholz. Gosh.
You had to reboot?
Yeah.
How long was the game?
Oh, it's happening again. All right. All right. So let's take the derivative now. Okay, the derivative here. X e to the x. Shh. There's been too many people talking. Y'all complaining that you don't understand anything. You're talking while I'm trying to teach.
I'm
Yeah,
listening.
They're horrible.
That back table needs to be broken apart, honestly.
What, the one with Cole and Anthony?
I mean, and they're awful routing.
I'm talking about the one in the back.
Can you calm down, you two?
The one by the
Yeah, one by the door. The ghosts of calculus past. All right. When I go to take the derivative, what do I have to use? The product rule. No, not chain. Product.
I'm mixing up what they're called. I know what to do, but I'm just mixing it up.
So product rule says fg prime plus gf prime. So f g prime. Well, derivative of e to the x is e to the x plus g f prime. What is derivative of x? 1. So there's my derivative, which in other words is e to the x times x plus 1. And the reason I factor that out is because I need to find where that equals 0 for my critical values. Now, does this ever not exist? No, the domain is all real numbers, right? So I don't have to worry about where it does not exist. I just got to set it equal to 0. So e to the x equals 0, x plus 1 equals 0. Okay, does that have any solutions? No, we looked at that at the very beginning. So x equals -1 is the only possible location of a maximum or minimum value. Let's run our increase-decrease test. Now we go back in here, remember, right? Back in here. So we go back into our derivative. Let's plug in -2. So we got e to the -2 times -2 plus 1. So -1. Well, negative, right? Negative. And I'm guessing the next one's going to come out positive. Let's plug in 0. E to the 0 is 1 times 0 plus 1 is 1. Positive times a positive is a positive. So I am decreasing from -infinity until -1 and increasing from -1 to infinity. Which means -1 is a what? Minimum. Let's go plug it back in. Spoiler alert, it's -0.37. And that goes back into the original. Okay, let's find concavity. Now I'm going to go back to this and find the second derivative. Because again, that's a product rule. F g prime, derivative of x plus 1 is just 1. Plus f, plus g f prime. So we have e to the x plus x e to the x plus e to the x. And you know what? I should have just factored it out right away. Because now when I go to factor it out, oh, yeah, that's gross. Hold on one second. Sorry. I should have factored it out right away. Because now I'm going to get e to the x, 1 plus x plus 1. So e to the x, x plus 2. There's f double prime. I think we did this problem. I feel like we did this problem way back when we started learning about the product rule.
Way back when to the degree.
Now, to find the points of inflection, I got to set that equal to 0. So I have e to the x equals 0, which we know what happens there. And x plus 2 equals 0. So -2. So we got -2. Let's see what happens to the left of -2. Well, this is always going to come out positive, right? E to the x is always going to come out positive, no matter if my power is positive or negative, right? Yeah, he's dozing off. He needs to get toothpicks into that. If I have -3, -3 plus 2 is going to come out negative. So positive times a negative is a negative. If I plug in something to the right of -2, say 0, that's going to be 1 times 2, 2. Positive. So that tells me that this is concave downward from -infinity to -2 and concave upward from -2 to infinity, which means that there's an inflection at -2 comma something. And when I go to plug it back into my original, -0.27. Let's graph. Okay. Now, y values that I need. Negative 0.27, negative 0.37, and 0. Those were all intervals.
Oh yeah.
Okay. X values that I need. Negative 2, negative 1, 0. Okay. So that tells me how to build my graph. You all right?
Yeah.
You okay?
Building.
Who we build?
I acted like I was important.
Fortnite.
For that reference. Yeah, that video.
Did you get it? The hit multiplayer game.
Okay, so we have an inflection point at negative 2, comma, negative 0.27. We have a minimum at negative 1, comma, negative 0.37. We have crossing through here. And we know that on the left side, as x goes to negative infinity, it's going to level off to 0. So minimum point, inflection. Now what's going to happen on the right side? As x went to infinity, what's the end behavior on the right side? As x went to infinity, it went up. Does it ever change back to going concave downward again? No, it's going to stay concave upward from negative 2 onward. So I don't know, maybe it curves up or something. I'm just going to make it look like it goes straight up. Probably doesn't go as linearly as I wrote it, but that's all that we know for right now. Okay, so that's the graphing piece. There's one other thing that I want to talk about, and that is slant asymptotes. Slant asymptotes, or what are called oblique asymptotes. Well, there are oblique muscles. Yeah.
No.
All right. Some curves have asymptotes that are called obliques. Now, for oblique asymptotes, there's only going to be one time where oblique asymptotes may arise for us, and it's in rational functions. I would jot this down for when they might show up. For rational functions, other types of functions do have oblique asymptotes, but the ones that we are going to look at are going to be rational. For rational functions, slant asymptotes occur when the degree of the numerator is 1 more than the degree of the denominator. That's the only time they could show up in a rational function. When the degree of the numerator is 1 more than the degree of the denominator.
When do Shady Shakes come to McDonald's?
February 20th.
Really?
I know that because Sadie said something about it. My Sadie night.
Okay, thanks for clarifying.
Yeah.
All right.
You better not ruin our tradition because of Sadie.
Yeah, I don't think he's alright.
Okay, so let's talk about slant asymptotes. How do you find slant asymptotes? Well, slant asymptotes will only occur in rational functions when the numerator is 1 degree higher than that of the denominator. Now, in thinking about rational functions, if the degree is higher in the numerator than the denominator, will it have any horizontal asymptotes? No, it's top heavy. It can't have any horizontal asymptotes. Will it have any vertical asymptotes? Maybe. Okay, but what we're looking at here is that this is the only possibility of them occurring obliquely or slanted. All right, I don't want to sketch the graph. I just want to find. Oh, these are the stats notes. I just want to find the asymptote, the slant asymptote. So I say sketch, but I'm not going to sketch this one.
Are we gonna find the obliquity?
The obliqueness. All right, so here's how we do that. We take the top and we divide by the bottom. Now, notice that I'm kind of leaving room here. I'm going to do long division, which needs every term represented. Oh, I'm sorry, I got them in the wrong spot. I put it like that. I don't know. If I don't do those zeros, I don't.
I forgot about this.
Yeah, it's not- So let's remind ourselves, we're going to do one like this, but the zeros make this a little weird. So we're going to do this one, and then I'm going to do one out of your homework.
Thank you, sir.
Okay, so reminder about long division. In long division, I try to make this first term match this first term, right? How do I make x squared look like x to the third? What do I multiply by? X. And I line it up just by putting this x over x. All right. Now, the rest of the trinomial gets carried along for the ride. X times x squared is x to the third. X times 0x is 0x squared. X times 1 is 1x. And then we subtract that entire trinomial. All right. So this cancels, this goes to negative 1x plus 0. Now, when can you stop long division? When the piece underneath the line has a smaller degree than the piece outside. Like here. We can stop long division now because the piece underneath has a smaller degree than the piece outside. So I know when I divide, this is x minus x over x squared plus 1. Remember, the remainder is the piece underneath divided by what was on the outside. So that's the quotient of these two things, right? It's x with a remainder of x over x squared plus 1. Now, I know an asymptote as I continue, a slant asymptote, as I make things go to positive or negative infinity, I'm going to be plugging infinity in for x, right? Watch what happens when I take the limit as x goes to infinity of negative x over x squared plus 1. What's going to happen there? What's that going to go to? It's going to go to 0. Because the degree on the bottom is bigger than the degree on the top. It's going to go to 0. So essentially, what's going to happen here? As I get bigger and bigger and bigger, that remainder is going to go to 0. That's going to happen every single time for a slant asymptote. The remainder is always going to become negligible. Okay, the remainder is always going to become negligible. Why? Because this degree was always going to be less than that degree. Always, every time. That's why you stop in long division, because the degree down here is going to be smaller than the degree here. So when I take it to infinity, when I say in the long run, I know that the line is generally going to go to just this piece without the remainder. So I know my slant asymptote is y equals x. That's my slant asymptote. In the long run, if I graph this thing, and then I graph the line y equals x, it would converge to the line y equals x. Okay. Let's do another one of those. This is number 62 out of your homework. I can't remember if I took it out of the numbers in your homework or if I just left it in and said you don't have to do it. So if 62 is in your homework set, you don't have to do it. First off, does it have even the possibility of having a slant asymptote? Yes. The degree on the top is 3. The degree on the bottom is 2. It's 1 off. 1 higher on the top than it is on the bottom. So I can say x squared minus 3x, and I say plus 0, divided by every term is there. So I don't need to add in any zeros. How do I make x squared look like 4x to the third? What do I multiply by? 4x. I like to put it right on top of the other x term. And then the rest of the trinomial is carried along for the ride. 4x times x squared is 4x cubed. 4x times negative 3x is negative 12x squared. 4x times 0 is 0x. I know it seems weird to write a 0x, but I don't know. It helps me line everything up nicely. It cancels my first term. That was the goal. Negative 10 minus a negative 12. Okay, negative 10 plus 12 is positive 2. Minus 11x. Bring down our plus 1 that was sitting in the end. Can't stop yet. My degree is not lower in my remainder yet. Okay, how do I make x squared look like 2x squared? Yeah, multiply by positive 2. 2x squared minus 6x plus 0. Okay, this cancels. Minus 5x. Negative 11 plus 6 is negative 5. And now I stop because the degree in the remainder is smaller than the degree in the divisor. So I say y is equal to 4x plus 2. Now I would write negative 5x plus 1 over x squared minus 3x. However, if I go in the long run, what happens to my remainder? So I can say that my slant asymptote is y is equal to 4x plus 2. Questions about that? Okay. All right. That's it for the day. That's it.